company produces 110 volts of AC. What's the maximum voltage here? So if you remember from the where's my paint pad? It's not opened yet. There we go. So if you remember from last time, the graph of the AC goes as follows. Sine graph. So this maximum and this average are two different things. It's root 2 times 110 is the maximum, is it? Yeah. So yes, it hits a max of 155.6 volts. Fair enough? Okay, so let's see, next. A 1 meter copper pipe is put on the ground east-west. A person picks up the pipe, flips it 180 and puts it back down. It takes 2 seconds to do this. What is the current? So what's happening here, if you were to look from the top, okay, there's a magnetic field from the earth going north, and the pipe lies perpendicular to it, which is good. There's the east and there's the west. And then someone picks up the pipe and flips it around. So what's happening here is, you could think about it two ways. I suppose you could think about it as either you're changing the magnetic field around the pipe, or the pipe is sweeping out an area within the magnetic field. I feel, for me, it's much easier for this to think about it as the magnetic field is being turned around the pipe. So you could almost think about the magnetic field being turned around rather than the pipe being turned around. In other words, I want to think about this as the B that's changing and not the A. Although, well, we'll just do it this way first. So there's only one pipe, so in the formula for the voltage, the N is 1. Oh, and which way will the current be induced? Well, which way is the motion here? This is maybe hard to see.
They don't know, so we don't have to.
Well, field is straight, and motion.
Up this way. It's when you want to change the motion.
Yeah.
Switching motion.
What? It doesn't matter. So anyways, there's only one N. We won't care about the direction. So we have change in flux over the time. Now we know what the time is. What's the time? 2 seconds. Now what is changing, the B or the A? I would like to make the B be the thing that's changing. So the A is going to...
They're the same.
You need the height. About diameter or something. That area.
Oh, well then we'll have to do then we'll have to do it as an area then, because okay. I suppose here there is no really. Let's see what happens. No, but what's really happening here, someone comes along and then flips the pipe around. So it doesn't really move off the ground.
No, he said fix up.
Yeah, but only just to turn it around. It's like this. He just goes, okay, anyways, maybe we'll do it with the area first. So it will be B change in area over 2. Now what's the B here? 0.07 10 to the minus 3 over 2. And then the change in the area. So what's happening here, well, what is happening? What area are you making? What are you sweeping out here? You're sweeping out a circle. So over the 2 seconds, you sweep out how much of a circle?
Oh.
Semicircle.
Well, not really, because if you now, I don't have any nice colours, but you have to imagine as this moves,
Yes.
there's a sweeping out here, and there's a sweeping out here.
Okay, yeah.
So when I flip it around, what have I swept out?
A
A
full
full circle. So the area is pi r squared.
What's up?
Well, this you definitely know. What's the or?
circle. 1.
No?
0.5.
Yes? Because it's a 1 meter.
R squared.
So you get a very small (27.5 microvolts).
I didn't think that way.
Yes, yes. There is other ways to think about it though. Just give me 1 sec. No, that's that one there. Then times that. Then divided by that. Here. No, I think this might be the best way to think about it. I was originally going to think about it as you're changing the magnet, but I think it's much easier to think about sweeping out a circle.
Yes.
Because you get one nice full circle when you rotate it. But I would like to do it another way too. I'm just trying to think of what would be another way to do it.
But you know, overhead says 5 rotates 180.
Yeah.
Still like beautiful.
Yeah,
If you
east-west, and this is still east-west. The pole's just upside down, but still lies east-west direction. Okay, actually, yeah, I think that's the best way to be doing it. Right, next one. A 2 meter, a 2 meter horizontal copper pipe is dropped from a height of 100 meters, and same deal. Right, so what is the EMF? So this is a lot like what example?
The last
Yeah, but it's also like the plane example.
plane.
The pipe is moving to the ground.
But you don't have any time.
No, but if only there was some way to work it out. Wait, I know. UVATS. So UVATF. It starts at rest, minus 9.81. The S is minus 100. Let's get the T. S equals U, which is 0, T, and then a half A T squared. So it'll take 4.5 seconds to hit the ground. Right, so what is changing here? The magnetic field or the area? The area is being swept out. So if it's 1 meter wide and it falls 100 meters, how much area does it sweep out?
200.
No,
100.
100.
The length is on.
The length is, oh, the length
Height
is
of-
2.
Yeah.
So it is 200. So in your face, KJ.
That's what you wrote there.
No, I didn't. There's a 2 there. Right, so it's going to be 4.5 here. The B doesn't change, it's 0.07 times 10 to the minus 3, but the area is the thing that changes. So we go from having no area swept out at the start to having 200 meters squared swept out at the end.
Can I ask something?
Yep.
Like, so far, the examples we have done, in every example, even either if you're changing in the speed, not speed, sorry, the area or the B,
Yeah.
but still, we're using comes up to using the same values.
What do you mean?
Like, for example, the always A is changing, we're still using 200. Okay?
The A is changing.
Just change it from the zero to
Zero to
Yeah.
in the exam, it's gonna can come, like something not from zero.
Oh no, the area that you sweep out always starts
like-
off at 0.
I mean, like, even in the B.
In the B. Hang on, let me just write this answer down. 3.11 millivolts. Okay, now what are you saying?
Like, in every example, we are just figuring out what's changing first. Okay, like B or A.
Oh yeah.
But
Yeah.
it's not affecting the values.
Well, I mean it is. Well, I mean, if the B is okay, you haven't seen an example where the B changes.
Yeah.
Yeah. So we'll do one of those. We'll make one up. Can I?
That's not what
No, I do understand what you're saying.
I'm
You're saying that you're saying it doesn't matter about the B. I know what you're saying. It's because you haven't seen an example where the B has changed and the area is not changing, and in fact the area. Yeah, no, I'll do. I know. I'll need to find an exam question because all the examples I could imagine is usually when things are moving. So when something is moving, it sweeps out an area. I need to get you an I think I have one. So, look, I'll give it to you in a moment, okay? Let's just go to, what's next? 4. In fact, maybe 4 is what we're talking about. A copper wire is wrapped around a circular loop 100 times of radius 5. The magnet is of flux density 2 is removed over a quarter second. What is the induced EMF? So, what's happening here in number 4? You have a magnet, north-south, and you have this pipe going around it or something like this. A 100 times. Now, here, in this example, the B is changing because at the beginning you have a magnet of 2 Tesla. And then what happens? You remove the magnet. So what is changing here is it's not the wire that's moving. It's the magnetic field which is moving, which is being changed. Okay? So we start off with 2 Tesla, and then what do we get at the end for the magnetic field? 0 Tesla. So how has the magnetic field changed? It's changed by losing 2 Tesla. So our formula E equals N with the minus, but I mean the minus just tells us which way it's going. Change in flux over change in time. Now what's the N here? 100. The flux is changed by 2. Again, I won't worry about the minus because I know how to work out the direction from using Lenz's law. And then the time, the 2. Now I need to put in the area, which I haven't worked out, but the area is not changing. The area is just a circle still.
So 1.5 squared?
Yeah. What did I say the radius was?
0.5.
So 0.025. No, the radius is 5.
Yes.
Okay. So I got here 6.28 volts.
The sign doesn't affect it?
I know it does, but I don't care about the sign because we have Lenz's law here. What's happening is the magnet is. Let me think about this carefully. What?
They removed it,
Say, yes.
then it goes back to 0, not -2.
No. 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 We have the magnet in there at the beginning.
Yeah.
So it starts off with 2.
Yeah.
And then when I remove it, what do I have?
0.
0. So how has it changed?
Oh, okay.
Yes, okay.
0, 1, 2.
Yes. Right. Oh yeah, so we can use Lenz's law to get the direction if we want. So we need to really think carefully here. I think the current should want to move. Right, you tell me before I write it down. Which way will the current move? If I remove the magnet, which way will the current move? To the left or to the right?
If you remove it,
Yeah, in other words, which way is this current going?
The same way with the arrow.
Yes, yes. Because the current induced will be against the movement of the magnet, the magnetic field. So the magnetic field is moving to the left. There's the magnetic field going around the magnet. It is moving to the left, so the current induced will be going to the right. Okay?
That's okay.
Yeah? Okay, let's go on to the next one.
just a second.
Okay.
6.2. Yep.
Yeah. Continue?
Yep.
Okay.
Exactly, good charger.
A small generator uses a magnet of flux density 5 Tesla. The rotating plane is 30 by 10 and it's rotating. So what you have here in number 5, you have your plane. Well, I'll draw it vertically first. And this is 30 centimeters by 10 centimeters. And it's in a magnetic field of, how much did I say? 5 Teslas?
Yep.
And it's rotating. And it rotates with frequency of 50 hertz. So that means 1 over the time equals 50. So the time for one rotation is 1/50th of a second, or 0.02 seconds, to do a full 360. What was my first question? What was my first question?
First question is what is the flux linkage?
The flux linkage. How many loops are there? Or did,
50. No, whatever.
or did I not say?
Didn't say.
Okay, well in that case then there's just one loop going around it, okay? Or, no, that's boring, nobody cares about that. Let's say 1,000 loops then. So there's 1,000 loops going around it. Okay, so the flux linkage, that's n times the total flux linkage is n times the flux, which is 1,000 times BA, which is 1,000 times 5 times 0.1 times 0.3. So how many Webers is that? 150 Webers. Why did I what? Oh yeah, well this is the total flux. It's n times the flux of one loop. Okay, what's the B part?
What is the flux linkage and flux 2 and the plane is horizontal.
Oh, so the first one when it was vertical. So this is when, what I just did, when the plane is like this. I wanted the flux. Hurrah! At the beginning the plane was vertical and the magnetic field was going through it like this, and I got the flux on this plane. What is the flux when the plane is now horizontal?
The same with the magnetic field. Zero.
Why?
Because it has to be perpendicular.
It has to be perpendicular. So if this is parallel, perfectly parallel to the field does not cross it. It has to be at least some angle. But if they're parallel, there is no flux through this surface. So,
I need to know the result
You do that,
the flux in the second position is 0 Webers.
Why?
Oh,
Yeah, you said why to him, and you answer.
when it is perpendicular, it's 150 Webers.
Okay.
There's 150 magnetic field lines going through the plane. When the plane is horizontal,
No, they're
none of
parallel.
these, yes, they're all parallel, none of them go through the plane. They just pass over it. There needs to be some angle. There is no angle when it's horizontal. But the other way to do it is by using the formula I gave you, which was BA. Now remember, it's the angle of the normal and the field.
Okay.
So this is, remember the formula is cos theta. So if I increase the angle by 90 degrees, what's cos 90? It'll be 150 cos 90, which is 0. So again, 0. There's no flux when they're parallel, only when they're at some angle. Okay. The next one is, what is the time taken to go from the vertical to the horizontal? What time is that? How long does it take to go from this position to this position?
We can use divided by.
Just give me the fraction or the answer. Yeah.
150 over.
Come on.
150 divided by 4.
What's the voltage?
Yes. In other words, this is the time for one full circle. So when we go from a vertical to a horizontal, that's a quarter of a turn. So it's 0.02 seconds divided by 4. 0.005 seconds. Lastly, D, I don't even need to look, I know what I'm going to ask you. It's what is the voltage that's induced? Now please, for goodness sake, actually listen to me this time. I don't need to put the N in this time, because what happened was the N is already in the flux because I put the N here at the start. So if I put the N in again, I have it done twice. The N has already been introduced at the start in my calculation of multiplying by 1,000. So there's no need for the N again, it's already in the flux calculation. So it's going to be, we go from having no flux, 0, to 150 Webers. So that's a change of 150 Webers, divided by 0.005 of a second.
Why?
Why what?
Why is it the time for just that part?
Because I'm only looking at it going from the vertical to the horizontal. So here, how much flux does it have? Flux linkage. 150 Webers. And here, how much does it have? 0 Webers. So it goes from 150 to 0 in 0.005 seconds. So the voltage here you get is 150 divided by 0.05, which is 3000 volts. Now this should not be surprising because at power companies the voltage is 10,000 volts at a power plant. So actually if I wanted to make this more realistic, maybe I should have said, instead of 1,000 loops, maybe I should have said like 3,000 loops or 4,000 loops. But anyway, power plants make high voltage power. This is an AC current of 3,000 volts. The reason it's so big is because it's spinning so fast and because there's so many loops around the plane. So 3,000 volts is not a surprising answer here. Okay. I don't think there's anything else really to say about that. Right, so what I want to do, I want to give you an exam question. Let me think now. Let's have a look at last year's, if there was an induction question.
Past papers?
Past paper. Well, let me just see. No, you might not have the one I am going to be looking at. So, Physics 2015. So let me see what they asked last year for the induction, if they did ask an induction one. Induction doesn't come up every year. It's, the next topic we'll do, the transformers come up a lot. Let's see. There now. There we go. There is a fairly straightforward question. They ask you for Lenz's law. Then they have this rectangle here. Wait, I think we did this one, didn't we? Or something like it. I think that's too easy. It's for babies. Let's find something difficult for men. Right. Young's modulus, cylinder. Yeah, now we're talking. So in this one here, you have this circular coil of 55 turns, radius 1.5 centimeters, and there's a flux density of 1/4 millitesla passing through it. Yes, okay, this is a good induction question. It's not too long to do. I think you could definitely do it now in like 2, 3, 4 minutes, and then I'll do it, okay? So this is what you get in the exam. Now look, how many marks for this question? 6. And in fact, it's an easy 6 really, because the formulas, there's not many formulas and they're not difficult to use. So what formulas would you need here? Let's say them first. What's the first formula you might need?
Flux, BA.
MBA for the total flux linkage. And then they ask you at the end, what's the voltage? So what formula is that?
Flux linkage over the time.
The change in the flux linkage over the time. You only require the N if you've not used the N in the calculation of the flux already. Any other formulas you need? No. The only other thing to state is... yeah, now just be careful guys, in the first one here, guys, the first one here is the flux, but that's only for one, BA, for one area, one circular cross section, whereas flux linkage is the total 55 circles of perpendicular intersection. So anyway, this should literally take you 1, 2, 3 minutes. I want you to do it now.